All right, good afternoon, everybody. We are almost at the end of 6004. So for the few of you who are here, I will remind you that we have a quiz tonight, and the details of which room you should go to are up here on the slide and also on our homepage. Let me also remind everyone, and you're going to hear this a few times in the next week or so, that all labs must be completed by Thursday of next week, as well as the design project. So please make sure to check your grades page and just verify that everything has been checked off. All right. So today we're going to kind of take a step back and talk about a couple things that we've assumed so far in the semester, but haven't had a chance to really delve into. So I'm going to start today by first, let's just do a quick run through of all of the things that we've learned here so far this semester. So we started with assembly language. The idea with starting with assembly language was to take the fact that you already knew how to program with a high-level language and bring it closer to the machine level. So show you how that's converted to instructions that the machines actually understand. We then went on to expand that to show you how we can support procedures in assembly language, and as a result also learned about the stack and the role that it plays in supporting those procedures. After that, we learned about binary representation. So everything we've assumed in this class assumes binary representation, so it's either a 0 or a 1. Those are the only two values that are allowed. And today we're actually going to focus on some assumptions that were made in order to actually make that be real, and how things actually work behind the scenes to make sure that we can do this. So then we went on to combinational circuits. We learned about logic simplification and how to make our combinational circuits smaller by using, the Boolean algebra axioms. After that, we were ready to move on to sequential circuits and actually be able to store state in our systems. We also started to learn about concurrency and how we could use BlueSpec in order to describe things happening in parallel. And then we got to the exciting part of processor implementation. So we built a machine that could actually run any program on it. And then we got into improving its performance. So we learned about memory hierarchy and caches specifically, and how we use caches with our processor in order to improve our performance. We moved on to operating systems and virtual memory. So this allowed us to handle things like exceptions, interrupts, running multiple processes safely on the same machine, being able to give everyone their own dedicated address space and not having to worry about them overwriting each other and things like that. And then finally, we got to pipelining, which is doing even more in parallel, and pipeline processors. And of course, once we're doing lots of things in parallel, then we also need to worry about synchronization. Okay, so that's a lot of stuff. You should feel really pretty excited about everything that we've gotten through in this one short semester. But I just want to highlight a couple things before the semester ends about some assumptions that we've made. So there are two things we're going to focus on in today's lecture. The first is, what assumptions did we make about our combinational logic gates? And so in order for combinational logic to work, it has to satisfy what we call the digital abstraction. And today we're going to learn a little bit about what this digital abstraction means and how we use it in order to be able to build combinational logic that works. The key to the digital abstraction is that we want to be able to have our combinational circuits deal with noise, and even when noise is added into our system, we want the circuits to be able to restore themselves to a good, valid representation of these zeros and ones, so that the noise doesn't accumulate and destroy the signal that we're trying to transmit. The second thing that we kind of took for granted is when we started to learn about sequential circuits, we said that in order for sequential circuits to work correctly, something had to be true about them. And specifically, what had to be true is that the data that's at the input to this, to all of our registers, had to be stable for a certain period of time. So we mentioned these terms, but really didn't do anything with them just yet. So we said that our data has to be not changing from t setup time before, before the rising edge of our clock till t hold time after the rising edge of our clock. And today we're going to look much more closely into what implications that has in terms of how fast we can actually clock our circuits and what constraints the fact that we need to make sure that our sequential circuits are actually going to work and transmit the right values has on our clock cycle. All right, so let's start with a digital abstraction. So what I mentioned was that throughout the semester we've been dealing only with binary values, zeros and ones, right? But we need to use something out there in our physical world to represent these digital values of 0 and 1. And the way that we do that is with voltage. Now, voltage is an analog value. It's a continuous value. And we somehow have to transform a voltage value into just these two discrete values of 0 and 1. So how do we do that? Well, you could think, you know, naively, that our first attempt might be to say something like, well, let me just establish a threshold voltage, which is what we call VTH here, or V threshold. And I can just say that everything that's less than VTH is going to represent a 0, and everything that's greater than VTH is going to represent a 1. Sounds pretty simple, right? In reality, it's not quite so simple. Okay, so let's see why not. Can anybody actually venture a guess as to what the problem with this simple implementation might be? Yeah?
Maybe if the voltage is near the threshold, then you might go between 0 and 1.
That's exactly right, right? What we said is we want our circuits to be able to tolerate at least a minimal amount of noise, right? So what happens if my voltage is just an epsilon, you know, less than this threshold voltage, and so I want it to be treated as a logic 0, but, you know, maybe I'm going to make a mistake and not be able to read it exactly and actually read it as this threshold voltage plus epsilon, and so I'm going to mistake this 0 to be a 1 when it shouldn't have been, okay? So here's our second attempt, which is that we're going to separate our low and our high thresholds so that we don't have the ability to make that mistake because of a tiny little epsilon of picking 1 when we wanted it to be a 0 and vice versa. So here, in the second attempt, I have two thresholds. I have a VL, which stands for my low threshold, and a VH, which stands for my high threshold. And now what I'm going to say is that every single value that's less than VL, I'm going to consider to be a valid 0. And everything that's higher than VH is going to be a valid 1. And everything in between, I'm just going to say is undefined. Okay? All right, so is this going to work? What do we think? Guesses? It's close, so we're getting in the right direction. And let's explore this further. So the first thing that we want to make sure is that we want to be able to have our combinational devices work even if we introduce some noise, because noise happens in our world, right? I mean, if I transmit something on a wire, I can't guarantee that I'm going to see on the other end of the wire exactly the same value as I put in on the input, right? So if I have a digital circuit that's going to produce something which is a valid 0. And let's say, that valid 0 was very close to my valid low threshold. So let's say it's, valid low minus some epsilon. And then I transmit it along this wire to my next circuit that I want it to become an input to, but there's a little bit of noise. And so this next circuit sees, instead of, voltage low minus epsilon, it sees voltage low plus epsilon. Okay, so now I've put myself kind of in that same problem I had initially between between confusing zeros and ones, except in this case, I won't confuse it to be a 1, but I might think that this is an invalid input, okay? And so how is my system supposed to behave if I have an invalid input? I really don't know. So what we want to do to address this is that we want to treat our outputs differently from our inputs. So specifically, we're going to have tighter constraints on our outputs than on our inputs. So in other words, we want to make sure that the functionality of our combinational circuits is such that they're able to take an input that maybe had a little bit of noise added to it and actually remove that noise from the system so that it's restoring our value to a good, strong 0 and 1 so that we can keep feeding the output of one circuit to the input of another circuit. So let's see how we do that. Okay, so we said that we're going to talk differently about our inputs and our outputs. So specifically, we're going to say that a valid digital output is a value that's, if you have a voltage, a value that's less than VOL, which stands for output low, then we're going to consider that to be a valid 0 output. Similarly, if my output is higher than VOH, which is output high, I'm going to consider that to be a valid high output. And on my line basically of this continuous voltage graph, I'm going to indicate here that somewhere towards my lowest possible value is this VOL, and somewhere on the other hand here is my VOH, and these are the regions of valid outputs. Now what about my inputs? What I want is I want to be able to say, like I mentioned, even if there's a little bit of noise introduced, I still want my input to be considered valid. So what does that mean? That means that my input thresholds have to be a little more lenient than my output thresholds. So on this line, the way that those are going to look is they're going to be a little closer to the center. And so what exactly is this telling me? This is telling me that VIL, the input low threshold, is slightly higher than the output low threshold, and similarly VIH is slightly lower than VOH. So what does that do for me? This allows this space in the middle here to be what we call a noise margin. Okay? And so it allows me to accept not an infinite amount of noise, but at least a small amount of noise such that my valid input is still, my valid output, when I add this noise to it, is still considered a valid input to my next device. And we continue with the concept that within this region between VIL and VIH, that is just an invalid value, and we just don't know what happens there. And so remember this inequality, which is it's always going to be the case that we want our VOL to be less than VIL, less than VIH, and less than VOH. All right. So let's take a look at, how does this help us in terms of restoring good values and dealing with noise. So we're going to start off by looking at an analog system. So suppose that I have some input, I'll call it VI, and some noise epsilon 1 is introduced to this input. And so my input to my F module is actually VI plus epsilon. All right? In an analog system, what would happen is that this F would see the VI plus epsilon, and it would produce some output that's proportional to that input, including the noise that was added. Okay? And now, I take this value and I add to it another little bit of noise, let's call it epsilon 2, and when I look at the output of G, it's now going to, you know, have been affected by both the epsilon 1 and the epsilon 2, and so you can see very quickly that as I'm trying to tie many gates together, this is going to be a problem, and, you know, potentially I'm going to start to misinterpret what my values are. So what happens in a digital system? In a digital system, the noise is canceled. So let's see how that happens, right? So I start off just like before, where I have input voltage VI, and I add some noise to it, epsilon 1, and that's the input to F. But the way that digital circuits work is that the output that F is going to produce is going to be the same as if that noise wasn't there. Okay, so it's going to produce F of V of I for me. Okay, so similarly, when they then go and see the next bit of noise, epsilon 2, G as well is not going to be affected by it, and the output that I get after both of these circuits is G of F of V of I, even though I had some noise along the way. Okay, so this is really crucial to understand. This is what makes our digital circuits work. So any questions about that before we move on? All right, terrific. So now let's ask ourselves a question of, well, you know, what do our circuits need to be made up of in order to be able to support this property, okay? And so basically what we're saying is the fact that we need to be able to cancel this noise means that our circuit elements have to be what we call active, meaning they have to have the ability of injecting energy into the system. And so what does that mean? That means that I need to have circuit elements like transistors, which have the ability to do that, whereas I cannot use an element like a resistor or a capacitor, which is a passive element, in order to achieve this. All right, so let's take a closer look at what we call the voltage transfer curve. So this is a plot of the input voltage versus the output voltage, and this is after, you know, all of the things have settled down. So it's not, you know, showing you intermediate changes as the value is changing from one thing to the next. And so specifically what we want to focus on are these thresholds that we talked about. So on the input side, we care about VIL and VIH. On the output side, we care about VOL and VOH. And now let's try to think about, you know, what a valid VTC or voltage transfer curve would look like. And so we're going to do this with a circuit element that we haven't actually used so much yet in 6004, but it's just a buffer. A buffer is basically the inverse of an inverter. So all it does is it transfers the same value. So a 0 fed into a buffer produces a 0, a 1 fed into a buffer produces a 1. All right, so what does that mean? That means that if I have a valid low input, I want to produce a valid low output. If I have similarly a valid high input, I want to produce a valid high output. And so the first thing we have to ask ourselves is, which portion of this graph is illegal for my curve to go through? Can anybody tell me? Okay, I'll tell you. So, oh, sorry. Hopefully you're probably going to say exactly that, which is that my curve cannot go through these red regions. Okay, so what do these red regions represent? These red regions represent a valid input because they're either less than VIL or greater than VIH, but an invalid output because I'm not producing an output that's either less than VOL or greater than VOH, okay? So my curve cannot go through here. And so, you know, what we expect is my VTC to look something like this, okay? And if we take a little bit of a closer look at the center portion here, you'll notice that the height of this white square here is always going to be higher than the width, right? Because of the definition of what VOH and VIH and all of these are. By definition, there's going to be more space between VOH and VOL than VIL and VIH. So what does this mean? It means that I have a slope that's greater than 1 in absolute value. In other words, I have a gain, or as we mentioned before, this has to be make use of an active component in order to be able to achieve that gain. The second thing that I want to mention is that in the region where we don't have valid inputs, my curve can actually do anything. So it could really look wacko like this. This is still a perfectly valid VTC for a buffer, because for all valid low inputs, it's producing a low output. For all valid high inputs, it's producing a high output. All right, so before we move on to our next topic, let's just go through an example to make sure that we understand this principle. So suppose that you're given this VTC here, and we want to identify what could be possible values for our low and high input and output thresholds. And I'm going to remind you of this inequality, which is that the order of the relative sizes must follow this inequality. And so how would I go about, trying to solve such a problem? So in this case, I'm told that my circuit needs to behave as an inverter, not as a buffer, okay? So this is exactly the opposite case from what we just saw. So now if I have a valid low input, I want to produce a valid high output, okay? So my V out is going to have to be greater than VOH. Similarly, if my V in is greater than VIH, meaning I have a valid high, it must produce a valid low output. So it has to produce something that's less than VOL. And so now I want to basically fit this curve to these inequalities. So the first thing, you can kind of ask yourself is, could my, VOL ever be a 0 in this device? What do we think? I see some shaking of heads, that's right. Why can it not be a 0? My device never produces a 0, right? No matter what Vin is, I can't produce a 0. So my VOL has to be something higher than 0. Now in general, I want to try to think about maximizing these noise margins, right? I want to give myself as much room as possible to deal with noise. And so I'd like, ideally, my VOH to be as low as possible, and my VOL to be as low as possible, and my VOH to be as high as possible, right? So looking at this graph, I see that the lowest output that it produces is 0.5 volt, okay? So I'm going to start off, evaluating this design with a VOL of 0.5. Okay, so what input voltages produce this VOL of 0.5 for me? If I take a look at this graph, I see basically that any input that's greater than or equal to 3 is going to produce this low output voltage, okay? So now I have 2 parameters to work with, and let's see if we can fill out the rest. So suppose that, I want to make now my VOH be as high as possible. I want to make it be 5. Can I make that work? What does my input voltage have to be in order to produce an output of 5? It has to be exactly 0, right? But I need to have a little bit of room to play with. So setting, my VOH to be 5 is too high for this device, right? So I need to set it to something lower, and I'm trying to figure out, what that lower value might be. So just to keep things simple here, I'm going to try 4 next, okay? So suppose that I try VOL of 4. I want to see if I can find a valid VIL such that this top inequality is satisfied and everything works well. So can I find a VIL that would satisfy this inequality and make this circuit behave as a valid inverter? Any suggestions for what VIL could be that would make this work? Yeah?
Just really quick on the slide, it's VOH equals 4.
Oh, whoops, I'll fix that, thank you. And also for anyone looking at the handout, this inequality was completely wrong. So please cross that out and correct it. Okay, so anyways, so we're trying to assume VOH is equal to 4. And so if I look at my plot here, I see that in order to produce an output of 4, I need my input voltage to be less than or equal to 1, okay? So if my VIL is equal to 1, then basically with these 4 parameters, I have a valid working inverter that satisfies this voltage transfer curve. Okay, so now I'm going to ask myself the question, well, so what's my noise margin? How much noise can this gate tolerate? And so the way that we think about noise is what's the difference between the input and the output low values, and similarly the input and output high values. So on the low end, we have a noise margin of 0.5, whereas on the high end, I have a noise margin of 1. And so typically, because we need our gate to be able to do both, we kind of think about the noise, what we call it noise immunity of the gate, as being the minimum of the two, and which would just be 0.5 with these specifications. Now, you might realize that, you know, if you evaluate this a little bit further and actually try to come a little bit further down this curve, you can find a point which will give you a different set of specifications that will give you a slightly higher noise margin. Okay, and so in general, the way we want to think about these things is how do we maximize our noise margin, and can we produce a gate that's going to achieve you know, the requirements that we have in order to, with the amount of noise margin that it's provided, still produce the necessary signals. Okay? Any questions before we move on to the second topic of the day? All right, terrific. So the second thing that we want to talk about today is sequential timing, okay? So this concept, actually, I mean, the other one's not simple either, but this one's even a little more complex. So let's work through it, okay? So the first thing I'm going to do is I'm going to remind you of the precise definition of propagation delay, and we're also going to learn about something called contamination delay. So we've talked throughout the semester about propagation delay, which is how long it takes for an input to make it through a circuit and to produce a valid output, okay? But more precisely, the definition of propagation delay is the following, which is it measures the maximum amount of time it takes for a gate to switch from one valid value to another valid value, okay? And we'll see exactly what that means in a second. Contamination delay is measuring kind of the opposite. It's measuring what's the fastest amount of time in which my input might change to an invalid value because something ahead of it became invalid, okay? And so that's known as the contamination delay. So let's look at it in more detail in this inverter timing diagram, okay? So on the top we've got V in, on the bottom we have V out, and our x-axis is just time, okay? So the first thing you'll notice is that this isn't exactly a square wave, right? In reality, things don't transition immediately from 0 to 1. There's, you know, a slope to these curves. And so when we're trying to think about what the propagation delay of a gate is, we have to think about, okay, as I'm transitioning from a low to high, what's the first point where my input became a valid high input, okay? And so I'm going to show you that here. That's this point on my curve, okay? And then the second question is, well, what's the point at which my output first became a valid output on this, became a valid low output. And so that is this point right here, which is when my output dropped below VOL. Okay? And so this time difference between when my input became its new valid input until my output reached its new valid output, that's the propagation delay. Okay, now this is only half the story, because this is only the propagation delay as our input changes from 0 to 1, and so we need to do the exact same evaluation on the other end. So on the other end, our valid input is down here when we just begin to have an input that's less than VIL, and our valid output is over here where we just get to an output that's greater than or equal to VOH, okay? And so if I measure that, that's my propagation delay on the other end, and of course we're interested in the maximum of these two because we want to know what's the longest amount of time that it can take, and so that defines that our propagation delay for this inverter is this TPD1. Okay? Any questions about that? Great. All right, so now let's move on to contamination delay. Okay? So contamination delay is going to measure the amount of time it takes from an invalid input to an invalid output. So what does that look like here? So here's my first point where, as I'm changing from 0 to 1, my input became invalid, okay? So it went above VIL, okay? Similarly, on my output, this is the point where my output reaches the transition between a valid input and an invalid input. And so here it becomes an output. It's hard to get all these straight. So this is the point where my output drops below VOH and becomes invalid, okay? So the time between these two is called the contamination delay, okay? Similarly, I do this on the falling edge, and I find another contamination delay, and here, which one do we think we care about? Which one would be my actual contamination delay for this gate? Yep. The minimum, exactly, because I want to think about what's the fastest that, you know, my input to some gate might no longer be valid because something else is starting to change, okay? And we're going to see in just a minute why we care about this. All right, and so my minimum one is this one here on the right, and so here I've figured out what my propagation delay and what my contamination delay are for this particular inverter. All right, so now let's think about why do we care. So if you recall, when we started learning about sequential circuits, we said what I mentioned at the beginning of lecture today, which is that our data has to be stable and valid for a certain amount of time around the rising edge of the clock, okay? So specifically, it has to be stable for at least T setup before the rising edge of the clock, and at least T hold after the rising edge of the clock, okay? If my input to my registers is changing during this time, then I'm not guaranteed that my register is going to behave properly and store the value that I want and transmit it on, okay? So I have to satisfy this in order to guarantee that my registers actually work, okay? So this is a huge assumption, right, that we just kind of made throughout the semester, which is that our circuits actually satisfy this. So today we're going to, dig a little deeper, and we're going to try to understand what exactly is the implication of satisfying this. So if we look at our output Q, what we're going to, there's, I guess, one other element that I want to talk about, which is what is considered the propagation delay of our register. So the way that we measure propagation delay of a register is from the rising edge of the clock until the output becomes a stable and valid value. Okay, so in these timing diagrams, these sections with red lines means that it's an invalid value, whereas the white sections are valid values. Okay, so basically this time over here, from the rising edge of the clock until I get to a new valid value, that represents the propagation delay of my register. Okay? Now, how do I go about meeting the setup time constraint for a sequential circuit? So we're going to look at a simple example. We've got here two registers. Let's call them flip-flop 1 and flip-flop 2. And you should notice also that the actual registers themselves might come from different technologies. So they themselves might actually have different parameters which you need to keep in mind. But for the purposes of just trying to understand these concepts, we're going to assume that all of our registers are the same. Okay, so what has to be true about my clock period in order to make sure that I'm satisfying my setup time? So let's take a look. So after my rising edge of the clock, the first thing that happens is my Q1 changes after TPD of this flip-flop, okay? And we saw on the previous slide that that corresponds to this time here, the time from the rising edge to when Q1 stopped changing. All right? Once Q1 reaches a stable value, then that becomes the stable input to this combinational logic, which we've drawn here as a cloud. And that's going to be what affects my, my input to my second register, D2. Okay? So the amount of time that it takes for D2 to reach its new stable value is another propagation delay of my combinational logic after the propagation delay of my register. Okay? So I need to allow in my clock period enough time for my register to transmit its new valid Q output, then for that Q to make it through my combinational logic in order to produce a new valid input for my next register. And then there's one last piece. What's that last piece? What else do I have to have time for in my clock period? My setup time, okay? So it must be the case that the input to the second flip-flop stops changing by T setup before the next rising edge of the clock, okay? So all of this together is going to tell me what my minimum clock period is going to be, right? So this tells me that my clock period has to be greater than or equal to the propagation delay of my register plus the propagation delay of any combinational logic that's between my two registers plus the setup time of my second register, okay? And I have to evaluate what this number is for every single register to register path in my circuit. And of course, the one that's the longest is what's going to control my clock period, okay? So we had a notion of this, and we've been talking about, trying to minimize our clock period, but the piece that we hadn't really taken into account is that aside from the propagation delays of your various components, there's also this additional piece, which is the setup time that you must satisfy in order for your registers to work properly. Okay, so what about our hold time, okay? So the hold time, as we mentioned, we care about the input not changing too quickly, okay? So what does that mean? That means that the propagation delay is not the value that we want to look at here. What we want to look at in order to think about our hold time is the contamination delay, okay? And this is why we introduced the concept of contamination delay. So what has to happen here? What has to happen here is that after the rising edge of the clock, I need to make sure that this input D2 doesn't get affected by the fact that new things are starting to percolate through this first register, okay? I have to make sure that I have some amount of time after the rising edge of the clock that these things still have no way of affecting this value right here at the input to my register. Okay? So if I look at my timing graphs, what does that correspond to? Well, I know that the fastest that Q1 is going to begin to change or to become an invalid value corresponds to TCD of my first register. Okay, and then after that, I have another TCD of my combinational logic before D could possibly become an invalid value. Okay, and so what does this mean? This means that I do have some room here, right? But the constraint that I have to satisfy is that the sum of these contamination delays must be greater than that hold time that my register needs to be satisfied in order for my register to work properly. Okay? So when it comes to t-hold, this is actually kind of complicated because there's nothing that we can do in order to change the value of t-hold. If I give you a circuit where the contamination delays, are less than the t-hold of a register, the circuit's just not going to work. There's nothing you can do about it. It won't work. Okay? And so this is a very important takeaway, which is that what these automated tools sometimes have to do is they sometimes have to introduce an extra delay between a register-to-register path in order to guarantee that the t-hold time of every single register in your circuit is actually satisfied. Okay, so let's, kind of summarize what we saw here. So what's controlling basically how fast we can clock our circuit? It has two very orthogonal factors. So the first is the propagation delays, which is what we've been focusing until now. And we have control about our propagation delays because we can choose, to put fewer things between our register-to-register path. And so, first of all, which flip-flop technology we use, that's going to certainly determine part of the story, which is the propagation delay of our register itself. And then the longest register-to-register path, including any combinational logic that sits between the two registers, is going to ultimately control my clock period. Okay? And so we know that we're going to have to look at every register-to-register path, and the maximum of those, including the setup time as well, is going to be what our clock period is. And if we have to, or if we want to lower our clock period, then that means that we have to reduce the amount of logic that sits between the sum register pair. Now, what about our hold time? Well, as I mentioned, our hold time, there's nothing that we can do about, okay? So that's just the only thing I could possibly do is choose to use another technology, another type of register that has a different hold time value, okay? But if it doesn't exist, then there's nothing that I can do about it. So it's very important that we ensure that in order for our sequential circuits to work correctly, our tools have to worry about this detail as well, and as I mentioned, sometimes add additional delays in order to ensure that the contamination delays add up to more than the required hold time. And so, just to give us a little bit of practice with this, I've put this sample problem from an old quiz. And, let's see if we understand how we would think about these sequential timing parameters. And so what I've given you here is a sequential circuit that has 3 registers and a bunch of combinational logic between them. And here you have all of the parameters for each of those gates. So you have a contamination delay, a propagation delay, and then for the registers, we also have a setup time. And we're actually going to have to figure out what that hold time might look like. Okay, so the first thing that I want you to think about is the clock period. So how do I go about figuring out what's, the minimum clock period that I can run this circuit at? So what do I have to allow for in one clock period? What do I have to have enough time for? So we said that we have to allow for the propagation delay of the register plus the propagation delay of any combinational logic, plus the setup time of the next register. Okay? And I need to look at this in all register-to-register paths. So in this particular circuit, I have, you know, this one path to look at, and then I have this other path to look at. Okay? And so the difference between these two paths is that in this case I have an AND gate, in this case I have an XOR gate, and so since the XOR gate has a higher propagation delay, I care about this upper path. Okay? And so this upper path is going to control my clock period, and specifically what it's going to tell me is that my clock period has to be larger than the propagation delay of this register, plus the propagation delay of this inverter, plus the propagation delay of this exclusive OR gate, plus the setup time of this register, okay? And in this particular example, that happens to be 880 picoseconds, okay? Now the second question that we want to ask ourselves here is, you know, what can we say about T-hold of this register that will allow the circuit to definitely work properly? Okay, so we said that T-hold has to be less than what? Yep. Then the sum of the contamination delays, okay? And so what paths am I going to be looking at here when I'm thinking about the sum of the contamination delays? Yep.
Looking for the shortest path.
The shortest path, exactly. So can you tell me which one might be the shortest?
The one that the second register going back to itself.
That's exactly right, okay? So the second register going back to itself has a contamination delay of the contamination delay of this register plus the contamination delay of this AND gate. If you look at any other register-to-register path, the contamination delay is going to be greater than that, okay? And so what does this tell me? This tells me that the hold time of my registers has to be less than that sum of the contamination delays. And so I can figure out that my hold time better be less than 130 picoseconds, otherwise the circuit is just not going to work. Any questions about that? Okay, terrific. So, so basically that's it for today. I wanted you to, you know, add this to your knowledge about 6004, which are these two, you know, very important concepts that make both our combinational logic and our sequential logic work. And we have one more lecture in 6004. We're not going to have a lecture next Thursday, but next Tuesday we will have one. And the topic is going to be cache coherence. Of course, this isn't covered on the exam, but it's actually quite an interesting topic. So we'd love to see you here for that. All right, thanks, and good luck to everybody tonight.